Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, glad to be here. Ready to dive into some fascinating stuff.
Excited to be here too, especially keen to unpack this particular topic. It's been generating a lot of buzz, but I think there's more to it than meets the eye.
Indeed. Always a pleasure to explore the gap between hype and reality. I'm ready to see what we can make of this Transformers and SAT solving research.
All right, so the paper we're focusing on today is Can Transformers Reason Logically? A study in SAT solving. For those who aren't deeply familiar, SAT solving, or Boolean satisfiability problem solving, is a classic problem in computer science. It basically asks, given a Boolean formula, is there an assignment of true or false values to the variables that makes the entire formula true?
Exactly. Think of it like a really complex logic puzzle. And it's fundamental because tons of real-world problems can be formulated as SAT problems, from verifying hardware designs to planning routes.
And what this paper essentially does is test how well transformer networks, which are these massive deep learning models, can tackle these kinds of logic puzzles.
Right, transformers are typically known for their success in natural language processing, powering things like machine translation and chatbots. But this paper pushes them into a different domain, formal logic. The question is, can they actually reason in a logical way, or are they just really good at pattern matching?
Well, the initial results were pretty impressive, right? They showed that transformers could solve a significant portion of the SAT problems they were given.
That's true. At first glance, it seems like a win for the deep learning can do everything camp. But I think it's worth digging deeper. The crucial question for me is, how are they doing it? Are they actually grasping the underlying logical structure of the problem? Or are they just memorizing patterns and regurgitating solutions they've seen before? That's where it gets interesting.
Okay, fair enough. But isn't pattern recognition a crucial part of intelligence? I mean, we humans rely on patterns all the time.
Yes, and pattern recognition is definitely important, but it's not the whole story. True reasoning, I believe, requires a deeper understanding of the rules and relationships involved. It's about being able to apply those rules to novel situations to generalize beyond what you've already seen. Can the transformer do that, or is it just limited to the specific types of problems it was trained on?
That's the million-dollar question, and I suspect the answer is leaning towards the latter. I mean, transformers are fundamentally about finding correlations in data. They're excellent at learning complex statistical relationships, but are they truly understanding the logical connections? Are they understanding cause and effect, the implications of different choices?
I see your point. So what kind of evidence would convince you that a transformer is actually reasoning logically and not just pattern matching?
For me, it would involve looking at the intermediate steps of the computation. Can we trace the decision-making process of the transformer? Can we see it explicitly applying logical rules? Can we quantify how its internal representations reflect the logical structure of the problem? If it can't explain its reasoning, or if its reasoning is just a black box, then I'm skeptical.
Exactly. Explainability is key. We need to be able to look inside the black box and understand why the transformer arrived at a particular solution. Without that, it's just an opaque system that spits out answers, and we have no way of knowing if it's actually reliable or robust.
And, frankly, I think the current architecture of transformers makes that incredibly difficult. They're designed to process information in a massively parallel distributed way. There's no clear separation between the different steps of reasoning. It's all tangled up in this giant web of connections. That's why I call it brute force. It works, sometimes brilliantly, but it's not elegant, and it's not insightful.
Okay, but even if it's just pattern matching, isn't that still a significant achievement? I mean, these are incredibly complex patterns, and the fact that transformers can learn them from data without being explicitly programmed with logical rules is pretty remarkable, right?
It is impressive, no doubt, but it's also potentially misleading. It gives the illusion of intelligence without the substance, and I worry that this focus on scaling up deep learning models is diverting resources away from other approaches that might be more promising in the long run. We have to consider biological constraints too.
I completely agree. It's like we're trying to build a skyscraper on a foundation of sand. The deep learning paradigm has achieved some impressive feats, but it's fundamentally limited in its ability to capture the kind of abstract reasoning that humans excel at. We need a more solid foundation, something that incorporates symbolic reasoning and explicit knowledge representation.
Precisely. We need to move beyond this purely data-driven approach and start thinking about how to build systems that can actually understand the world, not just memorize it. And for me, that means focusing on spatiotemporal reasoning, the ability to understand how things change in space and time.
So you're suggesting we abandon deep learning altogether?
Not necessarily abandon it, but augment it. I think there's a lot of potential in neuro-symbolic approaches, where we combine the strengths of neural networks with symbolic reasoning systems. We can use neural networks to learn patterns from data, and then use symbolic systems to reason about those patterns and make inferences.
Can you give me an example of how that might work in practice?
Sure. Imagine you're building a robot that needs to navigate a room. You could use a neural network to process the visual input from the robot's camera and identify objects in the scene. Then, you could use a symbolic reasoning system to reason about the relationships between those objects and plan a path for the robot to follow. For example, the symbolic system might know that you can't walk through a wall or the table is blocking the doorway. It can use this knowledge to avoid obstacles and reach its goal.
That's a great example. It's about combining the perceptual abilities of neural networks with the reasoning abilities of symbolic systems. And I think that's where the real potential lies for building more intelligent machines. To be able to explicitly represent and manipulate logical rules is crucial. So, neuro-symbolic approaches are exciting.
I agree. And I would add that we need to think about how to represent space and time in these systems. The robot needs to not only know where the objects are, but also how they move and interact with each other over time. That requires a different kind of representation, one that can capture the dynamics of the environment.
Okay, I'm starting to see the limitations of the pure deep learning approach. But what about the argument that with enough data and computational power, these limitations will eventually disappear? Isn't it possible that we can just brute force our way to AGI?
I think that's a dangerous assumption. It assumes that intelligence is just a matter of scale, that if we just build a big enough neural network and train it on enough data, it will magically become intelligent. But I think that overlooks the crucial biological constraints that define intelligence. The human brain is not just a giant pattern matching machine, it's a complex, interconnected network of specialized regions, each with its own specific role in information processing. And we need to understand how those regions work together to create intelligence.
Yes. And it ignores the importance of prior knowledge and innate biases. We don't come into the world as blank slates. We have certain built-in assumptions about how the world works, and those assumptions guide our learning. Deep learning models, on the other hand, typically start with a completely random set of connections. They have to learn everything from scratch, which is incredibly inefficient.
And it's also prone to bias. If the training data is biased, the model will learn those biases and perpetuate them. That's why it's so important to think about the data we're feeding these systems and to be aware of the potential for unintended consequences.
So, what are the specific limitations of transformers in the context of SAT solving that this paper highlights?
One key limitation is their difficulty in handling long-range dependencies. SAT problems often involve variables that are related to each other in complex ways, across long distances in the formula. Transformers struggle to capture those relationships because their attention mechanism, while powerful, is still limited in its ability to attend to distant parts of the input sequence.
Another limitation is their lack of explicit knowledge representation. Transformers don't have a way to explicitly represent the logical rules that govern the SAT problem. They can only learn those rules implicitly from the data. That makes it difficult for them to generalize to new types of problems or to reason about the underlying logic.
And I would argue that their lack of spatiotemporal understanding is also a factor. SAT problems often involve variables that represent events in time or locations in space. Transformers don't have a good way to represent those concepts, which limits their ability to reason about them.
Okay, so if transformers aren't the answer to AGI, what is? What are some alternative approaches that we should be exploring?
I think we need to take a more biologically inspired approach. We need to study the human brain and try to understand how it solves problems. We need to look at the architecture of the brain, the connections between different regions, and the algorithms that those regions use to process information. And then we need to translate those insights into computational models.
I agree. And I think we need to focus on building systems that are more explainable and transparent. We need to be able to understand how these systems work so that we can trust them and use them responsibly. That means moving away from black box models and towards systems that are more interpretable and verifiable.
And for me, it's all about spatiotemporal reasoning, We need to build systems that can understand how things change in space and time, and that can use that understanding to make predictions and solve problems. That means developing new algorithms and representations that can capture the dynamics of the world.
So, what are some specific research directions that you think are promising?
From my perspective, I'm really interested in exploring how we can integrate symbolic reasoning into neural networks in a more principled way. How can we give neural networks the ability to explicitly represent and manipulate logical rules? And how can we ensure that those rules are consistent and coherent? I'm thinking about developing new architectures that combine the strengths of both approaches, maybe something that uses neural networks to learn the parameters of a symbolic model, or that uses symbolic reasoning to guide the training of a neural network.
That makes sense. And what about you?
I'm really keen on exploring different neuro-symbolic architectures. I want to see if we can create a system that combines the flexibility of neural networks with the rigor of symbolic reasoning. For instance, how can we use neural networks to learn the concepts and relationships that are represented in an ontology? Or how can we use a symbolic reasoning system to verify the output of a neural network? I think there's a lot of potential in these hybrid approaches.
My focus is on developing new representations for space and time. I want to build algorithms that can understand how things move and interact with each other over time. I'm particularly interested in exploring the use of graph neural networks to represent spatial relationships and recurrent neural networks to represent temporal sequences. And I want to see if we can combine these approaches to create a system that can reason about both space and time.
Well, from my side, I am not ready to throw out deep learning yet. I think we need to push the boundaries of current models, see what they are truly capable of, and explore new architectures like mixture of experts. I think this study, while thought-provoking, is not a death knell, but a challenge to see where deep learning can adapt and to see the limitations of the study. This means creating bigger benchmarks, and even finding ways to combine neuro-symbolic techniques within the models, such as using a symbolic layer.
I agree, seeing where it can adapt is important. I'm also particularly interested in developing better methods for evaluating the reasoning abilities of these models. It's not enough to just measure their success rate on a particular task. We need to be able to understand how they're solving the problem and whether they're actually reasoning in a logical way.
Yes, explainability is key. We need to be able to open up the black box and understand what's going on inside. And that means developing new tools and techniques for visualizing and interpreting the internal representations of these models.
And we need to think about how to build systems that can learn from experience. Humans don't just passively absorb information. We actively explore the world, experiment with different strategies, and learn from our mistakes. We need to build systems that can do the same.
Right, reinforcement learning could be a key here, allowing the system to learn through trial and error, constantly refining its understanding of the world. It goes back to my point of more data and experimentation. If reinforcement learning is the correct path, then we'll need efficient ways to explore state space.
Exactly. This paper on transformers and SAT solving is a valuable reminder that we need to be critical of the claims being made about AI, and that we need to think carefully about the limitations of current approaches. And it also highlights the importance of interdisciplinary collaboration. We need to bring together experts from different fields: neuroscience, computer science, mathematics, philosophy, to tackle the challenge of building truly intelligent machines. It's a puzzle that will require all of our collective knowledge and creativity.
Agreed. The hype around AGI can be deafening, and it's important to step back and critically evaluate the progress being made. This paper is a good example of that, showing that even the most powerful deep learning models have their limitations. It's a call for more research into alternative approaches, and for a more nuanced understanding of intelligence itself.
And it reinforces the idea that AGI is not just a technical challenge. It's a fundamental scientific question, one that requires us to understand the nature of intelligence itself. And that means studying the brain, exploring different computational models, and thinking deeply about the philosophical implications of our work. It's a long and complex journey, but it's one that's worth taking.
I agree that we need to stay grounded and critically evaluate our progress. But I'm still optimistic about the potential of AI to solve some of the world's most pressing problems. And I believe that by continuing to push the boundaries of what's possible, we can eventually create machines that are truly intelligent and beneficial to humanity. Maybe AGI is farther off than we think, but I am still thinking of it as the end goal.
Well, that's all the time we have for today. Thanks everyone for the insightful discussion. It's clear that there's no easy answer to the question of how to build truly intelligent machines. But by continuing to explore different approaches and by engaging in open and honest dialogue, we can move closer to that goal. Join us next time on Cognitive Spirals for more explorations into the fascinating world of mind and machine.
Thanks for having me. Always a pleasure.
Great discussion, everyone. Thanks.
Indeed, a stimulating conversation. Until next time.